Okay, so here's my video guide on biplanar shading in Unity URP. This is for Unity 6. Now, I was absolutely shocked to find there was nothing online on how to do biplanar shading in Unity, so here it is. I took the time to figure it all out from scratch and put this together. Hopefully it can help someone out there. Before we get into anything else, if you don't know what triplanar or biplanar shading is, you need to look that up. Going forward, I'm assuming you already know what those are and what the disadvantages of triplanar shading are. The advantage of biplanar shading is you get almost the same result as triplanar, except you sample the texture one less time. So in triplanar, every single pixel in the fragment shader samples the diffuse texture 3 times, and it samples the normal texture 3 times, and any other textures you put in there, smoothness, metallic, whatever. It's going to sample each of them 3 times for every single pixel. Now, on a desktop, if you're building for desktops with discrete GPUs, this is 100% non-factor. They have colossal video bandwidth. You do not need to worry about this. But if you are building for a constrained platform, say VR or standalone or mobile, then this can be an issue. You can very quickly hit those video bandwidth limits. So, for example, the Quest standalone, the Quest 3 standalone, really, really powerful GPU, but the GPU bandwidth to the memory is very, very low, and that's because the memory is shared with the CPU. So it's not like normal video memory. It's very slow, and it's very limited in what it can do. So cutting off one of those samplings can be fucking huge performance gain. But if you're building for desktop, you're not going to see any performance gain whatsoever, so don't bother. All right, now that that's out of the way, let's talk about the monoplanar really quick. As I said, I'm assuming you already did know about this. Monoplanar, this is regular. You have to UV unwrap it. You can't be a procedural anything. You get these ugly seams where the seams meet together, something like a sphere. But you're going to get the best results with just regular old unwrapping and UV mapping stuff. Triplanar, right out of the box, you can see it's quite a bit blurrier and muddier. You lose a lot of the detail and the coherency as things sort of blend together from the different axes. And then you'll see the true biplanar and the hacky biplanar. They look almost the same as the regular triplanar, but we'll get into the differences in a minute. Also, another thing, the triplanar inside shader graph is far and away the simplest because there is a triplanar node. You just make a triplanar node for your albedo, a triplanar node for your normal, you hook them up and you're done. It's that simple. So again, if you're building for desktop, don't bother with biplanar. You only need biplanar if you're building for a constrained platform where video memory bandwidth is a bottleneck. Okay, let's move on. Now here's what I'm calling true biplanar. What it does is we manually do all the math that happens inside the triplanar node, but we do it in the shader graph, and then we only sample the 2 most prevalent textures. So for example, if we're looking from like the front top, say this pixel right here, that's going to sample and blend between the top and front projection, and it's never going to sample from the side. And then if you're looking from like the front left, it's going to sample the front, and it's going to sample the left, and it's not going to sample the top. So you lose one texture sample. Now there's advantages and disadvantages to that. As I stated earlier, you use less video memory bandwidth, but you also get a very slight visible seam. I don't know if you can see it. There's a very, very slight seam. Now this seam in triplanar gets, smoothed over with that third material, but if you're not doing the third material, you're going to get a slight seam there. But as you saw, it's like a very, very minor seam, and you cut down your video memory bandwidth by 33%. It's a big deal, but whether or not it's worth it is up to you. If you're building for desktop, again, this is not for you. You don't need this, just use triplanar. And then we've got this hacky biplanar, which does not have the seam that the regular biplanar has. You get rid of that seam, you don't have it, but the disadvantage is you can only view it from 2 angles, front and side. If you view it from the top, it looks horrendous. Now, why the heck would anyone ever want this? Well, if you're building, and this is the whole reason I got into biplanar in the first place, if you're building a terrain auto material, which is what I was doing, and you have a cliff face, which is a rocky texture that only gets displayed on faces that are somewhat vertical, not flat, like you'll never see them from the top because they're cliff faces, then this is perfect. It's way simpler than the true biplanar. It's way simpler than the triplanar, and you get no seams. It looks fantastic if you're only looking at it from these 2 angles. You look at it from the top, it looks awful. So we're going to go through all of these, and I'm going to start with the hacky biplanar first. So first things first, to make a custom shader graph, you right-click in your project window, create, you're going to go down to shader graph, URP, lit shader graph, and then call it whatever you want. It's up to you. So let's take a look inside the hacky biplanar. All right, here's the hacky biplanar. This is what it looks like. Not that complicated. We'll go through this node by node and explain what everything does so that you understand it, so that when we get to the true biplanar, which is quite a bit more complex and it has a custom node with a bunch of custom shader code, like we'll get into all of that, but we're gonna do the hacky one first just because it's simpler. And the triplanar, the full Unity supported triplanar, as you can see, is just 2 freaking triplanar nodes. It's so simple. You just hook them straight into the color and the normal and whatever else you have, the mission, whatever. It's super simple. So if you don't need bilinear, don't use bilinear. It's not worth the headache if you don't absolutely need the performance uplift. Okay, into regular biplanar. Let's hop into this. So the first thing we need to do is we actually need to go into the graph inspector. That's this little circle with the eye in it at the top right. To get that to show up, go to graph settings, and then in the graph settings, down where it says fragment normal space, you want that to be world. Let me quickly go over, just in case you don't know. There's 2 different shaders. You got a vertex shader and a fragment shader. The difference between this, fragment is the face, vertex is the point. Vertex, this is shaders for like making trees, like leaves sway in the wind. That's all vertex shaders. Fragment shaders is things like the colors and the metallic and the smoothness and blah, 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 blah. So we're working in fragment. So fragment normal space, we want to set that to world because we're not using the built-in UVs. We're calculating our own UVs. So we need to tell it that we're doing that. Okay, right off the bat, first thing we're going to do is get the world position. You do that simple right-click, create node, type in position, see geometry position, double-click that, get it in there, set it to world, and then you can click this little up arrow to make that disappear. Okay, you're going to plug that into a multiply node by dragging out, typing multiply, and we want multiply A. If you do B, it's fine as well, just auto plugs it in here. You can switch it either way, it doesn't matter, multiplication doesn't care. And now we're going to plug in the scale value. Now to add these, you're going to open your blackboard, and the blackboard is this little X icon at the top right. You're going to hit the plus, and you're going to add a float, and you're going to call it scale. And I already have one, so it named it something else. You're going to do that again. You're going to make a texture 2D, call that albedo or base texture. Another texture 2D, you're going to call that the normal or the normal map. And then another one, float, and you're going to call that blend. Now these all show up in the material when you make a material. So you're going to, after you've made this shader graph, you're going to right click, create material, whatever it is. I'm going to call it test met. Okay, great. And then we go up here where it says the shader, it defaults to the URP/lit. We're going to drop that down and do a search for whatever the one that you made is. So I've called mine biplanar. So I do a search biplanar and there it is. You select that and now it's using your biplanar shader. Go ahead and delete that. I don't need it. Okay, so we've got our inputs. Once you've made your material, you click on your material. Where is it? Monoplanar? No, biplanar. Here we go. You'll see you get these inputs. So I've got the scale, the albedo, the normal, and the blend. So when you make texture 2D, it lets you put in a texture. And one quick thing, in case I forget later, your normal maps, you need to select them and make sure they are normal map. This lets the engine know to treat these values as being between -1 and 1. If they are default, they are treated as between 0 and 1. You will get improper normals if this is not manually set to normal map. It won't know what to do, it won't read it correctly. Okay, so with that out of the way, world position multiplied by scale. And that output, we're going to put it into a split node. And we're going to split the RGB. So we're getting our world position RGB. That's RGB in this situation is X, Y, Z. So our world position X, Y, and Z. And this is for the pixel. The part of the face of the mesh where this pixel we're rendering hit. We've got the world position X, Y, Z. So the first thing we need to do is we need to calculate the UVs for that position. Now, since we're going biplanar and we're using the hacky method, we know that we know we're doing front and side every time. We don't need to take into account top. We don't need to take into account which of the two, top, front, and side, are the most anything. We already know it's the front is Z, the side is X, and that's all we're ever using. We're never going to use top. So we can use the world position X as our U value and the world position Y as our V value. U and V's are the X and Y axis on a UV map. So that's why for this front Z-axis, it is X and Y. You can see UV X is here is X and Y, and on the side, UV is your Z and Y because we're looking at it from the side. Y is still up, but to the right is now Z, which is forward because we're now looking from the side. So taking the X and Y, which is R and G that we split, put it into a vector 2. Again, just drag off and type in vector. You'll see vector 2, X, Y, it doesn't matter. It's just where it's going to auto plug in. You're going to make your R to X, G to Y. Now this gives you your front UV. And then do the same for your side UV, where your G, your Y value, is going to plug into the Y value here, except we're adding this 0.5 offset. Now, I don't know how well I can show this. I'm going to try to show it really quick. So on a triplanar, this is the one disadvantage of triplanar other than the bandwidth, is that you can get, here we go, right there. All right. So you see how there's this two black lines right here and here, how they kind of mirror each other, and you get this V shape. That's the big disadvantage with triplanar. It's taking the same texture in from the left, in from the front, and from the top. And so you can end up in situations where the edges perfectly line up and you get this sort of mirrored seam like that. Again, it's not a big deal. It's kind of hard to see if you don't know what you're looking for, but we're getting rid of that because on Hacky Biplanar, it's super obvious when you see that seam there. So all we're doing is we're offsetting it. So the front texture is going straight on, and the side texture, we're actually pushing the texture down a little bit so it's offset. So you'll never ever see that seam. You'll never be in a situation where they sort of mirror and you get this sort of weird like inverse mirrored texture. That just doesn't happen because we put that offset in. You don't put that offset in, you get that. So just quick little offset, quick dirty little thing. Okay, so the UVs for the front axis are going to plug into two texture sample 2Ds. These are our front and side views. So drag in your albedo, drag off that, type in sample texture 2D. You want sample texture 2D, texture T2. This is the one you want. You don't want LOD. We'll get into that later. But for this hacky one, you just use regular texture 2D. Set the type to default, the space to tangent, and then you pull out your RGBA and you put it into a lerp node. So you're going to pull it out, type in lerp, and you want lerp A, not B, not T, lerp A, just like that. And then do the same for the side texture. You're going to pull off your side UVs and plug them into another sample texture 2D, exactly the same, using the same albedo map, pulling that the texture out and into the B of the lerp. Now the T of the lerp, the thing that decides how much of A and B to blend together, like what the weight of them is some little bit more complicated math, which we can go ahead and get into right now. So I'm dragging this line all the way down here. We're bypassing the normals for a minute, and we're going down here to decide, is this the front texture? Is this the side texture? And how much of each? So we're going to get our normal vector, create node, normal. You should see normal vector, not face normal, not any normal unpack. You want normal vector. Set it to world space. Go out and split it. We want the R and B. Now this is the X and Z values. X. So normal vector, what that is an arrow that points off of the face. So the pixel that we hit, what direction is the face pointing? And we're going to look at the X and we're going to look at the Z to figure out which one's bigger. And we're doing that by taking the absolute, because sometimes it can be negative, right? We can go in a circle. We can look at X negative and Z negative. So we need to take the absolute. We don't care if it's negative or positive. We just want to know which one is the larger value, which one's furthest away from 0. We're going to take that absolute and put it into a power node. And then we're going to blend each of those with our blend value. This is what's going to determine, let me go ahead and show that really quick. This Hacky Biplanar Matte Blend. So I've got my blend set to 1.2 on the Hacky. If I set it down lower, right, you'll see the seams show up. This is what the textures look like when you're just projecting straight on. Actually, let me set that to like 0. There. This is the way it looks when you're just projecting straight on. You see this left side is stretching across the front, and the front texture is stretching across the sides. So this blend is going to let us tell it like we want even less. Like right now, it's you'll see this, the side texture is very powerful and the stretching is very weak, but because the stretches are so long, they're very apparent and you can see them. The blend is going to fade those out so that when you're looking from the side, it favors the side texture more. And when you're looking from the front, it favors the front texture more. Now this is a float, so you can change it, because if you set it too high, you see you start getting a seam. And this black, if you ever see this black blob, that's it's called a NaN virus, N-A-N, not a number. It means something went wrong with the math, and the result of some of the math ended up being something that it couldn't understand, so it just drew it as black. If you're seeing black, that's why you went out of bounds of the math. But you also end up with this very hideous seam. So you need to manually deal with your blends to find something good. Like 1.2 on the Hacky looks, I think it looks fantastic. It blends all huge area in the middle, and then this front area where it's the worst, it cleans it right up. So back into our biplanar material, we've got our two power nodes powered by the blend, and now here it gets a little weird. We're going to take the output of both our powers and add them together, and then we're going to divide by the R one. So R is absolute, power, and divide. They both get added together and then divided by the R. That's going to give us the proportion of how much R, which is the left. So if it's side, it's a higher number. If it's front, it's a lower number. That comes up here and plugs into the LURP, which this was our front, this was our side. So remember we said if it's a higher number, it's a 1. We're going to take more of our side. If it's a lower number, it's the front. Yeah, lower number is more of the front, higher number is more of the side. And it will LURP between those. And then we output of our LURP straight into base color. And if you do that, you hit save, you go into your scene, you should see your material right away. You won't have normals, so your lighting won't look great, but you will have an object there. Now getting into normals is a little bit more complicated. All right, sorry for the quick cut. While I was explaining my normal logic, I realized I had done something really dumb and was doing math and multiplying it by 1 for literally no reason. So quick optimization here. Let's back up. Front UV, plug into sample texture 2V. Side UV, plug into sample texture 2D. This one's using our normal texture, not the albedo. And the type is now normal, space is still tangent. Again, make sure your normal texture is actually set to normal in the inspector. Otherwise, it will do the math wrong. If it's not set to normal, it will treat the values as between 0 and 1. If it is set to normal, it treats the values as between -1 and 1. That distinction is very, very important. Make sure your normals are set to normals. All right. So for the front face, you're going to take your R channel and you're going to build a vector 3 with it. Just drag it off, type in vector 3. You want vector 3x. It'll give you a vector 3 node, and you can wire everything up. R goes into X, G goes into Y, not plugging anything into the Z value because the blue channel, the Z value, is going to do some extra stuff. We're going to multiply that, which the blue channel is how far the normal sticks up. So this particular pixel we're looking at, how far should it appear to stick in front of the face rather than being pushed into it or flush with it. So we're going to multiply that by the normal vector in world space. Right-click, create node, normal vector. None of the other normal strengths, none of that unpack normal. You want normal vector and set it to world space. You're going to multiply those together. That's going to allow us to modify the Z component, so how far out this is sticking from the face. And the nice thing about this is it will also take into account the negatives for us, so we don't have to do any math at figuring out whether or not we need to flip it for the back side or anything like that. Using the world's normal will do that for us. So we multiply our B by the total normal vector, so this gives us a vector 3 output, which is why we had to make a vector 3 here. Yeah. So we add them back here, then that puts the RG back with the B, and then you also bring in the R and G from the normal vector from the world as well. Those all get added in together. But it's only the Z that we want multiplied, which is what happens here. Okay, so you add those together, and that goes into another lerp, and the T from this lerp comes from the same place. We reuse the same logic that we used in the albedo map. It's the same T. You want exactly the same T, otherwise your normal map will not match your diffuse map. This makes it match. Okay, and then do the same for your side face, except now you're using your side UVs instead of your front UVs. Normal, tangent, multiply the world normal vector by the B channel, bring out your R and G channels into a vector 3, and then add them back together and lerp on the B. Real quick sidebar, I totally forgot when I was making this shader, you need to normalize the output of the lerp. That is because we did math on it, so it may be a magnitude greater than 1, so we need to renormalize it. Plug that into your normal world space. All right, you do that, and your hacky biplanar is done. You throw it on your object, and you are good to go. Okay, so that was the hacky, the one that doesn't quite look right from the top, but it looks fantastic from the sides, and it's super cheap and easy to run. It's less math than the true biplanar. Now let's get into the true biplanar. This is the more complicated one. This one's going to come with a code block you're going to need to download. I uploaded it to GitHub. You just copy and paste it, really quick and easy. But the as you can see, the node is quite a bit trickier. So let's go ahead and get into this. First thing, we're going to go into our graph inspector, go to our graph settings, and again, fragment normal space. You need to set this to world or this will not work. And then inputs, you need a few more inputs. So we need a float for sharpness. We need a texture 2D for the albedo map. We need a texture 2D for the normal map. We need a float for tiling value. We need a float for the MIP bias. And we need a float for the resolution. Do we need the MIP bias? No, we don't need MIP bias. Okay, you can delete that one. That was from a previous iteration, and then I ended up rolling that logic into the custom function. So there used to be a bunch more nodes down here to calculate MIP maps. You don't have to do that anymore. Okay, yeah. So this one, same thing. You would just right-click your inspector, create shader graph, URP lit shader graph, and create your whatever the heck. Same way, name it whatever you want. Make sure you have these nodes, and we're going to create this custom function now. So to create a custom function, what you're going to do is you're going to right-click, and you are going to create node and type in custom, and you will see custom function. Here we go. You're going to name this custom function right here, or sorry, type, switch it from file to string, and then in the name, you're going to name it biplanar logic, just like this one is named biplanar logic. Okay. And then you've got this list of inputs and this list of outputs. Now this inputs and outputs is very, very sensitive to what you write. It has to be written correctly, and it has to be written case sensitive. The order, not so much. The order doesn't care about, but it has to be case sensitive. It has to be perfectly written, and it has to match this code. And so to get this code, there is going to be a link in the description to GitHub, and that will take you here. And this is a GitHub gist, so it's just this one. You can download it or you can copy paste it. You just basically select all of it. Is there a way to select all? I don't know. Raw, what does that do? There we go. Control A, Control C. You come in here. If you set this to string and you named it biplanar logic, you go down to this box and you just Control V, paste it in there. Now you're going to start getting a bunch of console errors because it's looking for all these inputs and outputs and we haven't set them up yet. So go ahead and set them up. You're going to hit the little plus icon and you're going to add inputs till you get all these. The first one's going to be normal. Again, this is case sensitive. Everything has to be right. Normal is a vector 3. World pause is a vector 3. Sharpness is a float. Resolution is a float. Tiling is a float. And we go down to outputs, and we start adding outputs. UV underscore A is a vector 2. UV underscore B is a vector 2. Blend is a float. T, uppercase T, lowercase a is a vector 3. Uppercase B, lowercase a is a vector 3. Uppercase T, lowercase b is a vector 3. Uppercase B, lowercase b is a vector 3. And MIP level with a capital M, capital L is a float. Now, like I said, I don't know if I said it. I've had to record this a few times because I keep making mistakes. But the true biplanar, what this does is we have to manually do the math that's automatic inside this triplanar node. We have to do that manually. So that's what all these TA, BA, blah, 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 all that crap. It's for all the math that we have to manually do in order to do this. And also, this is actually slightly more complicated from a user perspective than the triplanar, but it's not actually more complicated to render it. So in a triplanar, you just have 3. Like, it's hidden from you, but so this is the albedo, for example. You see we got our albedo map. There's only 2 of them. That's important. If there was a third, even if it contributes nothing, right? We put it in the lerp, and the lerp is always 0. It never contributes to a single pixel in the fragment shader. Because it's here and it's wired up to something, it would sample it. So in order to be able to delete one of them and get our biplanar, which is, full 3D texture rendering, but only ever sampling 2, we can only have 2. Now that's a problem because we need to render from the top and the front sometimes. Sometimes we need to go from the top and the side. Sometimes we need to go from the front and the side. So these actually swap around. Sometimes this is the top, sometimes it's the front, sometimes this is the side, sometimes this is the front, whatever. And in order to get them to do that, we have to push all of our computation before we get to the textures. So that's why we have all of this, because we need UVA and UVB to switch depending. So sometimes UVA is the front face, sometimes it's the side face, and so on and so forth. And there's also some other things that happen with this biplanar. You get some weird, like, pixelated seams that we need to take care of, and that's because of the MIP mapping. Because we're swapping UVs, like we're taking, UVA might be the front face for this texture, and then the very next pixel over, it's the side face. And so the UV, the only way it knows that is because the UV changed. But the shader sees this massive change in UV, or sorry, rather, your GPU sees a massive change in UV and it freaks out and it says, oh my God, this thing just stretched super far, or it moved really fast, or something weird happened. And so it defaults to the lowest MIP map level. So you get this like solid color pixel line going straight across your material, and it's super messy and gross. So we have to do some math to manually let it know that that's not going to happen. We're going to tell it on purpose what MIP to use. And so you'll notice here we have sample texture 2D LOD. And I told you earlier we were going to get into the LOD. The other one was the regular biplanar. The hacky one is regular sample texture. The true biplanar is sample texture 2D LOD, because we have to manually specify the MIP maps because we're swapping UVs between textures, and that will confuse the shit out of your GPU. So we have to do that math manually. All right, so after you've created your custom function, you've made it string, you've got the name right, you've put in all the code, you've got all your inputs, all your outputs, all your console errors have cleared up, you're ready to keep going, we can keep moving on. Create a normal vector, world space, plug that into the normal input on your custom function. Get your world position, and if you're using a floating world, you would add in your offset. So you would put in your floating world offset in here that gets pushed from a script. Add that in and go push that into your world position. Sharpness, again, just your float sharpness, plug that in. Resolution, plug that in. Tiling, plug that in. Resolution, this float resolution is something kind of annoying that we have to do. Let me set the default value. This is 1024. So what this resolution means is, this is the one really annoying thing about true biplanar. With a triplanar, when it does the math for the MIP maps, it just knows the size of the texture and it knows how to handle the MIP maps. Because we're doing that math manually, we need to know the size of the texture, but the shader doesn't expose that. So we need to input it manually. And you only have to do this once when you make the texture, but see, true biplanar matte, you'll see, let's see, resolution 1024. That's because this image that I have selected, Cliff's albedo, if we go to it, how do I get to it? What is it? Hold on. Here we go. Select. Here we go. So if I click on it, let me type in Cliff. Here we go. Cliff albedo. You'll see right here it says 1024 by 1024. So this is a 1K image. So I put resolution 1024. If it's a 2K, you'd put 2048. If it's a 4K image, you put 4096. If it's 512, you would put 512, whatever. I think that's how it goes. I think that's what you're supposed to put in. It doesn't look messed up. Yeah, it looks fine to me. So what happens is if you get this wrong, you see how, man, I hope it shows up, but this is like really like sharp pixel. You've got really high contrast, whereas the ones next to it are smooth. Especially if you move really slow, you'll see it like shimmers and it's sparkling. That's because it's using the full MIP level. And so we need to manually compute this so it doesn't do that. And in order for the shader to do that efficiently, we need to manually feed in the texture. So 1024, something close. Even if you put the wrong value and you put 2048 and it's a 1024, it's okay. It's not a big deal. It's only going to be slightly off. You probably won't even notice. All right, so let's go back into our true biplanar. You plug those into your custom function, and it's going to choose UVA or UVB for us. Let me go back into the code really quick, and I can show you what that means. There we go. So, right, it's doing all this math. If if this one's higher than that one or whatever, then we know X is the winner. X is the biggest one. So we output UVA as the side UV, and then UVB will either be front if UVB will be top if the Y is greater than the Z. Otherwise, UVB will be the front. Yeah, so top if it's bigger. So it's just a bunch of switchboard logic. It'll handle which UV is for which texture. And again, we have to do that before we run the texture because we can't have 3 texture sampling. We can't have a texture sample for the front, the side, and the top, and then just not sample one of them. The shader graph won't let us do it. If we put a third sample texture in there, it will sample it. Okay. So you've set this up, you've got all your inputs, you got all your outputs, all your things are gone. Let's move on. We've got our sample texture 2D LOD. We just went over why it needs to be LOD, what that means. Type is default, space is tangent. We've got our albedo plugged into the front and the side. Well, they're not really front and side, but they could be either. So we're going to call this A and B. So the A1 and the B1, because it might be top, it might be front, it might be side, we don't know. You take your A UVs and plug them in here. You take your B UVs and you plug them in here. And then the LOD is coming out here from MIP level. MIP level is going to plug into your LOD for both of them. And then just like with the hacky one, you take your output texture and plug it into a lerp. Now, notice this one is flipped. The UVA is plugging into the B. The UVB is plugging into the A. That's just because the way the switchboard logic worked out. It's not a big deal. Just switch them. Just do it. It's not worth trying to figure out how to get it the other way around. It's just not worth it. Just put the A into the B, put the B into the A, and then that plugs into your base color. And that's it for the albedo map. Very simple. And again, the lerp comes from the blend. So on your custom function, pull out the blend. That's the T value for your lerp. All right, now we're getting into normals. These normals are quite a bit more complex. So again, sample texture 2D, we need an A and we need a B. Type is going to be normal space tangent. The UVs, we get our UVA into the top one, we get our UVB into the bottom one, and then the same MIP level goes into our LOD on both of them. Now, the math is going to get a little complicated here. Just keep with me. The R channel on UVA, you're going to pull that out and put it in a multiply node. And the R channel on UVA is going to get multiplied by TA. So pull off a TA, multiply that by the R channel. The G channel is going to get multiplied by BA. And then those two, you're going to add the result together. Now the B channel, we're going to multiply it by normal vector world, just like on the hacky one, for the exact same reason, because we want to preserve the normal of the mesh, and we just want our normal map to modify it. So normal vector world multiplied by our B channel, and then we're going to add that back into our R and G channels. So now we've reconstructed the normal, taking into account the normal vector. And then plug that into a lerp node. Again, this UVA plugs into lerp B. And then the T value of the lerp comes from the same place, the blend node. Now on UVB for the normal, here we go, UV underscore B uses the same blend, the same MIP level, same normal map texture. The R channel is going to plug into a multiply node, and the R channel multiplies against TB. The G channel is going to plug into a multiply, and that multiplies against BB. Once those two are multiplied, you add the result together. And then the B channel, just like with the UVA, we're going to take our normal vector from the world, multiply it to the B channel, and then add that back into the R and Gs, so that we've got our unified normal. And that plugs into the A of the LURP. Now when we output this, we need to normalize it to bring it back into the range of, so with an albedo, right, you can have 1, 1, 1, and that's okay, because it's red channel, green channel, blue channel. It doesn't care. With a normal, it's a vector. So the result of R, G, and B dot magnitude should be 1. So we have to re-normalize this because we just did math on it, and the result of X, Y, and Z might not be 1. So we do a normalize on it, and in the output, we plug into normal world space. Just like with the hacky one, make sure you've gone to graph settings, fragment normal space, and set it to world. And that should be it for your true biplanar shader. Man, I hope that fucking helps somebody. Holy shit, this took me a long time to get through. Just recording the damn video took forever. Let me know if you need any help, and I will do what I can to help you.